Hello and welcome to NPTEL MOOC on Applied Electromagnetics. In this module, which is more for an entertainment, of course you will have to follow the arguments to be really entertained by this module, we consider what is called as a quasi-static field. Okay, we try to answer, can an ideal capacitor exist? What do we mean by an ideal capacitor? I mean, from circuit theory, we know that if I have a capacitor of some value C, then if I put in some current I and maintain a voltage V of t across this capacitor, then I know that the relationship between V, I and C is given by I of t is equal to C dV of t by dt, right. We do not worry about what is the shape of the capacitor, what is the capacitor made out of. If there is an ideal capacitive element, we expect the relationship I of t to be equal to C dV of t by dt, where C is the capacitance of the structure. Okay. But can really this equation be justified physically? I mean, do we actually have an ideal capacitor? Let us see why this equation is not complete picture, why this is only an approximation, and how does this approximation break down as we increase the frequency of the operation. That is, we assume that the potential V of t that is maintained between the capacitor plates is of the sinusoidal form, and as we increase the frequency, what happens to this equation? Okay. The realm in which we are going to operate is what is called as quasi-static field. We have already seen one region of operation when we talked of a transmission line, where the length of the transmission line or the dimension of the transmission line along its length was much larger compared to wavelength. Okay. So wavelength was actually only part of the transmission line. So the transmission line usually was of a very long length compared to the wavelength of the light that we were using. Okay, that is one extreme. Then there is another extreme, as we discussed, which is known as a geometric limit, where the dimensions of the devices are very small, whereas the wavelength of the light is very large. That dimension is the circuit theory. Somewhere in between is what we have in the form of a quasi-static. So here charges, potential will be varying with time, current will be varying with time, but not so fast that one has to consider the effects of delay between when the source changes its distribution and the field correspondingly responds to the changed distribution. Okay, something that you will be seeing later on as we talk about waves. Okay. So for now we understand that charge distribution could be changing, the current distribution could be changing, but they are not changing so fast that if the charge Q of t is kept here and it is varying very slowly with respect to time, so that you have a Q of t, the electric field still remains more or less like a Coulomb electric field. So you will have Q of t by 4 pi epsilon naught r square. Okay. So this kind of a variation is what is called as a synchronous variation. In a synchronous variation, we assume that the fields are tracking the changes in the distribution of the current or the charges in a synchronized manner. Okay, no phase delay or no phase lag appears. So Q of t changes, E of t also changes by the same thing. Okay, of course this is an approximation, because in reality you will have to consider the fact that the source distribution changing will take some time to be affected to the electric field. Okay. So let me go back and write down the plates over here. So these are the plates that I am considering, and to this plate I connect an external potential or a voltage generator V of t or an EMF generator V of t, which will supply a current I of t to the plates. We assume that the plates have a radius of a, and therefore their area A, which is pi a square, will be much larger than the separation between the plates h. Okay. I have shown you in some sort of a weird geometry, but you have to imagine that these are actually some nice circular plates. Okay. So I have a nice circular plate. Okay, so nice circular plate, and then these plates are separated by a very short distance h. So A of the plates, that is area of the plate, is much larger than the separation h. So current is being pumped in. What happens to this current? Current, if you remember, is the flow of charges. So the charges keep flowing, and then they now come to the conducting plate, top conducting plate, and of course these charges are removed, or essentially negative charges are deposited, because the current has to return back to the voltage generator V of t. So there will be positive charges on the top plate, there will be negative charges on the bottom plate, there will be no charges in the region in between, which is characterized by having a permittivity epsilon and a permeability mu. Okay. So there is no charges in between. So what happens to the charges? The charges will uniformly distributed. Okay, they will get uniformly distributed over the entire plate. Okay. So that is what is going to happen, and we will assume that. Okay, we will also neglect any fringing that might occur on the outside edges of the capacitor. So there won't be any fringing fields over here at the edge. So all the charges are deposited uniformly, and because of this you would expect electric fields to be generated in the region in between. Okay, and that electric field will also be uniform. So this would be the electric field that you would be seeing, or rather the D field that you would see, and these D fields will be all in the direction downwards. Okay, so which we will denote by the unit vector E over there. So what are the relationships that I am looking at? As I said, the D field is following the charge. Okay, the charge deposited on the top plate will be Q of t, the charge deposited on the bottom plate will be minus Q of t. Since I know the area of the top and the bottom plates, there will be a surface charge distribution rho s, which is given by Q of t divided by A, and we know that the surface charge distribution, okay, must be equal to the D field because of the boundary condition. So the boundary condition tells you that the D field must have the surface area rho s. Where is the boundary that I am looking at? Well, you know, I am actually looking at this particular surface. You can imagine that I actually have a surface over here, okay, and coming out of that surface will be the D field, which is all perpendicular to this surface, okay, and that would be equal to whatever the charge distribution that you are going to see. The charge distribution will be surface charge distribution given by Q of t by A, and that is exactly equal to the charge D of t that you are seeing. What would be the electric field E of t? Well, electric field will be D of t divided by epsilon. So this would be equal to Q of t divided by epsilon A. Now let us try to relate this electric field E to this V of t. In order to do that one, I consider, you know, one particular path. This would be one path. I go all the way up to the edge and then come back. I also consider an extension of this path. I am assuming that this extended path, which I am denoting by this, you know, cross marks that I am making with this red color pen, okay, is not very far away from the edge. Okay, so this length that I am considering is actually very, very small. So essentially it's just outside the capacitor. Let's also label these points as some A, B, C and D. Let's label this as C prime and D prime. Now if you imagine, you know, going through this path A, B, C and D, right. So through this path if you now travel and evaluate what is the integral of the electric field, right. So I know that integral of the electric field, integral E dot dl will be equal to whatever the total EMF that would be surrounding. Okay. This is a very important thing. This EMF is coming essentially because of the static, almost static electric field. There are no magnetic fields inside the region as of now. So if I evaluate this integral for the paths A, B, C, D, what I get is E of 0, which would be the electric field on axis. So this is the axis at rho equal to 0, rho being the radial distance from the center point that I am considering, center line that I am considering, times h, because that is the height, minus the side ones do not contribute to any EMF. Therefore you now have E of A into h. So this one is the on axis field and this is the edge field. Okay, we don't consider fringing effects, as I said. So this is the on axis field, this is the edge field. The difference between these two on the path ABCD must be equal to 0, indicating that the electric field at any point, if you consider, must be exactly equal to the electric field on the axis itself. So we have a uniform electric field happening. Unfortunately, if you now try AB C prime D prime, of course not unfortunate, try AB C prime D prime, the corresponding field E of 0 comma h will be equal to V of t, because that is the potential in this picture. As you go from C prime to D prime, you see a potential of V of t that would be equal to the potential on the line AB. So on this loop, this equation actually allows you to find out what is the on axis field, which would be the same field everywhere throughout, and that would be given by V of t by h. but we've already calculated what is the on axis field. This is given by q of t by epsilon a, correct? So I can put that expression over here and then write v of t by h equal to q of t by epsilon a. Adjusting this equation gives me v of t into epsilon a by h equal to q of t. I am not done yet. I know that I have a top conductor, right, to which there is a incoming current I of t and there is a certain surface around that, so which is what we considered. So there is a closed surface, in fact, around this one there is a closed surface to which we are sending in the current I of t. What is happening as a result of sending current I of t? The charges inside are changing, right? So if the charge distribution or the charge is q of t, then I know that I of t must be equal to dq of t by dt. This is from the continuity equation, correct? So from the continuity equation I know that I of t equal to dq of t by dt. I know what is q of t, which is v of t into some term in the bracket. So I can write this as I of t equal to epsilon a by h dv of t by dt. And if I identify this epsilon a by h as capacitance C, then I have I of t equal to C dv of t by dt. Seems everything is fine. So what was it I was talking about? I mean, I have shown you that there is an ideal capacitor, but is this the complete picture? I mean, is this the correct picture to ask for? Unfortunately, we have neglected a major thing that is going on in the dielectric region between the capacitors. What is it that we have neglected? Well, we have said that there is a D field between the top plate and the bottom plate, right? So the D field is supposed to be uniform, but the D field is varying with respect to time. If the D field is varying with respect to time, then D or del D by del T, which represents the displacement current, will not be constant, or it will not be zero, it will be varying with time. And del D by del T by the current continuity equation will take over the role of the conduction current whenever conduction current is zero. Of course, in the region between the capacitor there is no conduction current, but as a result of D of t varying with time, there is a displacement current. Now what does the displacement current do? It will actually generate a magnetic field around you like this, or around the current like this. So this is the direction of the current, and these fingers tell you the direction of the magnetic field. We will calculate some of this in the next how to calculate magnetic field in the next few modules, but Ampere's law tells you that if there is a displacement current or if there is any form of a current, there will be a magnetic field. Okay, so let us look at those fields. I will call this as first order, okay, and we will call the previous one as the 0th order. You will soon see why we are calling these as different orders. So for the first order, I need to find out what is the electric flux that is being generated in the dielectric region between, and I need to find out what is the displacement current, which is the flux that I am going to find out, and then d psi e, which is the electric flux, that I have to differentiate this one with respect to time. So again, go back to the problem that we have. This is the top conductor, and now what I do is I consider a closed surface. Okay, so I consider a closed surface like this, which actually has a radius of rho, okay, where rho simply tells me, so this central line is the rho equal to 0 line, and rho equal to rho will be the line at which this particular closed surface ends. There are charges, there is d of t, and surrounding this or coming out of this closed surface will be the electric flux density psi e, which is integral of this d of t times the surface ds. Okay, and what kind of a surface we are considering? We are considering a surface of, what is the surface area of this one? D is perpendicular to this fellow, and d of t we have already found out what is that, right? So we know d of t is given by q of t times a. So if I apply Ampere's law, which tells me that, and there will be magnetic field surrounding this, right? So that is the electric flux, and there will be magnetic field surrounding this. There will be different magnetic fields. So I am considering the magnetic field at a radius rho. So that will be h of t, because there is a time variation out there, times 2 pi rho, which is what your left hand side of Ampere's law will tell you. This must be equal to d psi e by dt. Okay, we already know what is the area of this, right? So the area that I am looking at is pi rho square rho being the radius of this closed surface. So pi rho square and times whatever the D field that I have, right. So what is the D field that we have? We know what is the electric field from the previous example, or from the previous this one we know what is the electric field. E is given by V of t by h, okay, and therefore the D field, D is given by epsilon times E, and E is V of t by h. Therefore I can write this as V of t, so epsilon by h V of t, that must be equal to 2 pi rho into h of t, okay, which gives me the magnetic field H will be circulating this one. So I will call this as some H vector. So it would be circulating, and this rho cancels out, rho cancels here, pi cancels, pi also cancels. So you get epsilon rho divided by 2h dV by dt. So clearly V of t is not constant, and dV of t by dt will also be not constant. So you get h of t equal to or proportional to the first derivative of V of t. And it is very important to note that this H field is non-uniform, which means that the H field actually will be 0 on the axis, but it will keep increasing linearly at the edge where rho is equal to a. This is not the end of the story, because if I have a magnetic field in this way, there will be a magnetic flux also in the same direction. And what is the magnetic flux do? This magnetic flux is also now changing. So this changing magnetic flux will introduce a change in the EMF along the loop that you are going to consider. So there will be a change in the EMF because of the change in the magnetic field. Who tells you that? Faraday tells you that. The Faraday's law tells you that if I go back to the path, A, B, C, D path, please refer to the previous this one to find this particular path inside. So instead of taking this CD path at the edge, I will consider the path to be at some rho equal to rho itself, and then write down what is the electric field change. I will have E of 0h minus E of rho, which is the electric field at this particular point rho, or on the line rho along C and D. H will be equal to minus d by dt of magnetic flux. Where is the magnetic flux coming out? Well, the magnetic flux is coming out because this is how the magnetic fields are coming out, right. So the magnetic fields are curling, and therefore they are coming out of this particular loop. So imagine, go back to this picture. This is the top plate, this is the bottom plate, this is what you are actually trying to evaluate. So this is the height h, okay. So the magnetic field is circulating and coming out, and that will introduce a certain flux. So you have to find the flux over this surface area ABCD. I will leave this as an exercise for you to show that the magnetic flux is given by mu epsilon by 2, okay, rho square by 2 dV of t by dt. Okay, this is essentially integrating the non-uniform magnetic field over this loop ABCD. You are going to get the magnetic field. Of course, what you want is d psi m of t by dt. If you want this one, you just have to differentiate the potential a second time, so you get d square v by dt square. So clearly this would be what is called as the second order effect. So this flux change or the EMF change should be equated to that expression which we have written. So you can rearrange the equation and write E of rho minus E of 0 to be equal to mu epsilon by 4h, okay, rho square d square v by dt square. This is a very important thing. What it tells you is that the electric field is not uniform anymore. The on axis field and the field at off axis, or away from the axis, is actually different. How large is the difference? In order to find out, I first need to know the on axis field. Now here is an important caution. The on axis field will not be the same as that we have calculated earlier, okay, because the earlier calculation assumed that electric field was uniform in the path AB, C prime, D prime. Here it is not uniform. So in order to find out that, I need to apply the Faraday's law or apply the EMF condition only at the boundary, where on the edge, if I take on the edge, E of A will be equal to V of t divided by h. So I can substitute for rho equal to A in this expression and then find out what is the on axis field. I will find this as V of t by h, which is good thing that you expect this, but you do not expect this correction, which is mu epsilon divided by 4h A square d square V by dt square. This allows you to go back and then write the field at any radius rho and time t to be equal to v of t by h, which is what you would expect in the uniform case, but there is a correction, minus mu epsilon by 4h a square minus rho square d square v by dt square. This implies that E field is not uniform. This is a very important thing, because when you look at the sketches of a typical capacitor, okay, in most undergraduate studies on circuit communication, if you look at, the electric field is assumed to be uniform, except of course there is a fringing, but we have anyway neglected the fringing. So you see that the electric field is taken to be uniform, capacitance is very nicely defined, but the electric field is not uniform. The electric field changes as you move away from the axis. Okay. To give you some numbers as to how this will change, assume that the plate radius A is about 10 centimeter, and we are looking at a frequency of about 100 megahertz, which is fairly small frequency, okay, f equal to 100 megahertz. We will also assume that V0 is about 100 volt, okay, this is a fairly large volt, but if you now calculate what would be the EMF at any distance inside the capacitor at a distance of rho, this would be equal to E of rho into H, okay. So you can find this one by substituting for rho, or you know what is the equation for E of rho, that would be V of t minus mu epsilon divided by 4, that H has gone on this side, a square minus rho square into d square v by dt square. If I assume that this is a sinusoidal signal V0 cos omega t, then d square v by dt square will be minus omega square v naught cos omega t, right, because that is the second derivative of this one. And what is the EMF on the axis? EMF on the axis at rho equal to 0 will be equal to V of t itself, which is V naught cos omega t. So if you look at the change in this potential, okay, the change, we will represent this as delta EMF. This change is given by the term that is actually giving you the change, so which is the correction term mu epsilon divided by 4 a square minus rho square d square v by dt square. Sorry, this should be rho equal to 0 here, because that is where we are looking at the change. At the edge to the on axis change will be this particular quantity. So if you evaluate this, this will turn out to be approximately 3.3 volt, which is about 3% of 100 volts. It's not something to be laughed at, because I ask you to do the same thing at f equal to 1 gigahertz. You will be surprised to see what is the change in the EMF. Why would you be surprised? Because if you keep all the other parameters same, then the change in the EMF is actually going as a function of this d square v by dt square is nothing but omega square V0, right. So there is maximum change I am talking about, not the actual change in respect to time. Maximum change you see is that is proportional to the frequency square. Now frequency, if you increase by 10-fold, this change will happen about 100-fold, okay, and that will be a quite a large change. In fact, many of the, the entire theory that we have derived will no longer be correct when you are operating this one at a 1 gigahertz for this particular system, okay. So it's actually something that you have to keep in mind, that all the definitions that we have seen of a capacitor is strictly valid at very low frequencies, because if you redo the calculation for the EMF at f equal to 50 hertz, you see that the change will be very small. It won't be 3%, it would be very small, because you are pulling down the frequency by a very large factor. So to sum up, the capacitor that you see on the equation that you see I of t equal to c dv of dv by dt is really a low frequency approximation, and the corresponding circuit that would look like this for the physical picture of large capacitor, okay, would be equal to a capacitor in the circuit theoretical approximation where current I of t is flowing and the potential V of t is maintained, is a very simple picture. As the frequency or at the picture at low frequency, as the frequency increases to the gigahertz range, then what happens is, you can show later on by a simple extension of the exercise that we are going to do, that there will be an inductive component added to this, and this inductive component comes because there are leads which are taking the current into and outside of this capacitor, okay. And further, if you assume that the dielectric inside is not an ideal dielectric, but it actually allows you a small conduction current of sigma E of t, then you will also have to add an extra resistor to this. this would be the correct picture for this scenario. Okay, so there will be a capacitor, there will be an inductive component. I have not shown you how the inductive component to be calculated, but this would be proportional to d cube v by dt cube, that is it would be proportional to the third order effect, and there would be a resistor which would directly be proportional to how much is the imperfection in the dielectric. So this is a picture that is usually used at high frequencies or at RF radio frequencies and above. So at millimeter wave frequencies or at other places, the capacitor that we think is a very ideal element will no longer be an ideal element just relating I, C and V, but it will also have to be modeled as capacitor, inductor and a resistor. Okay. So I hope you have come away with a very important fact that physical scenario is different from what is in the mathematical approximation. Mathematically an ideal capacitor can exist because that is just a relationship between I and V. You postulate that relationship, say that this is the relationship that exists, that can easily be done. But if you postulate that, you are neglecting a lot of other things that is happening in a real physical capacitor, and that recognition that you can't just get away by writing I of t equal to C dV by dt, and you have to include a term corresponding to an inductor and a resistor, because the physical system is not the same as the mathematical system, is the essence of this story. Okay. So I hope you have been entertained with this, and I will show you how this other equivalent circuit came in the exercise and the problem sheets, and from the next module onwards we will look at how to calculate the corresponding inductance of the structures that we saw earlier. So for example, coaxial cable capacitor we have calculated, we will now calculate inductance and so on. With this, thank you very much.